Hello again, and let's continue on with the second part of our lecture on functions. So today we're going to spend some time talking about some common types of functions and what they look like graphically and some of their properties. And then we're going to get into some examples of how we can actually describe functions. So when we look at a graph, can we actually figure out sort of words to use to describe that function maybe to someone else. So let's go ahead and jump right into it with some common functions. And we've seen some of these before. So what we've got here, these are the simplest versions of all of these functions. So for example, a line. We've got a linear function. The simplest version of that would just be x, right? Notice we're using our function notation here, that new f of x. But really we just have x. That's about as simple as you can make it. That's a line. Maybe I could add 3 to it, or I could give it a slope of 2 or something like that. But just for now, it's just that's our line. We should be pretty comfortable with those. We've been dealing with lines for a while. What we also have is a parabolic function type, and I commonly just versed as a parabola. And we've got the simplest version there, just x squared. So f of x is just equal to x squared. And we're familiar with exponents. We know that if we take x squared, that's just taking x and multiplying it by itself. So this is another common function. We've got the square root function, and we know how to deal with those. Again, at its base, at its simplest form, just square root of x. We don't have to have anything else in there. Deviating away from sort of names that you might be familiar with, we have the inverse function, and that's the function 1 over x. So we've got the x on the bottom. And then I have two versions of exponential functions here. They're both exponential functions. There's nothing special about either one of them. This first one is f of x equals 2 to the x. And so there, the base is 2. So the base is a constant, and the exponent is your variable x. And so whatever x might be, you're going to put that as the exponent. And here, I just have 2 as my base. For here, this exponential, I just have e as my base. And this can get confusing. E is actually just like pi. So just like pi, we say it's approximately 3.14. E is approximately 2.71. It's just another number like pi, where it's just this 2.71 pops up so often that we just have decided to give it a letter, and so that we can just write that letter instead. Very similar to pi. What can get confusing here, though, is that pi isn't an English letter. And so when you see it, you recognize, oh, okay, that's pi, that's 3.14. But E is an English letter, and we hopefully now are so used to using letters as variables that a lot of times when people see E, they think it's a variable, but it's not. E it pops up so often that we just give it that designation E. And so if you see the letter E, you know that means 2.71. So just sort of calling out to that here. Again, no difference in these two exponentials. They're both exponential functions. I just like pointing out the special sort of case for E, if you will. Great. So we've got all these common types of functions. These are the 5 functions that we're going to be looking at. Let's take a look at examples of how we might write these equations out. So let's start off with a linear function because we've been dealing with these for a while. So when I have all these letters A, B, C, and D, these are just constants. They're just numbers. And because I don't want to be specific, I don't say what numbers they are yet, because they can be any number that I want them to be. And that's just what we mean by they're constant. So they are a number, but because we're not dealing with a specific equation yet, I don't actually put in with the numbers. They're just kind of like placeholders. So for example, I could have f of x equals 3x plus 2. I could have, here, let's not squeeze that in so much. Like I could have 3x plus 2. And in that case, my a would be 3 and my b would be 2. Just a placeholder. I'm just using a and b in place of 3 and 2. Or maybe I say negative 2x minus 5. And then, again, just placeholders, negative 2 for a and negative 5 for b. So the reason that I have all these a, b, c, and d all on all these equations is to show you how I can sort of manipulate these function types, these linear functions, these parabolic functions, square root, inverse, exponential. It's just showing you how I can manipulate them, and it doesn't change what type of function it is. So for example, if I take a function, if I take my x squared, right? We saw before that x squared is a parabolic function. It's a parabola. Well, if I multiply that x squared by a number, that doesn't change it. It's still a parabola. And that's the point that I'm making with this a. And then even more so, if I add bx plus c, if I add something multiplied by x, and if I add another constant c, it still doesn't change the fact that this is parabolic. So this is sort of the general format of any parabolic function. You'll have some number multiplied by x squared plus some number multiplied by x plus a constant. And plus just some number, I should say. And so there we go for a parabola. With a square root, again, I can take my square root of x right here, and I can multiply the x by some number, call it b. I can also add to that another number, call it c. And then after I do all that, I can even multiply that entire square root by a number, call it a. And then at the end of all of that, I could add another number, d. And so if you saw something that looked like, for example, 3 square root of 2x plus 5 minus 6. This is still going to be a square root function. Really, we just have all of these things here that are sort of extra added in. And I kind of, for now, don't really care about them. I just noticed that, hey, there's still this is still a square root function. And we can keep going on with an inverse and an exponential. I don't think I need to do too much explanation of what the a, b, c, and d mean in here, just showing you how you can sort of manipulate these and still keep them at the same function type. So there we go. Let's go ahead and look at a parabola and actually a graph of it. I won't bother with lines because we've been graphing those for a while now. So we've got a parabola here. And as you might expect, if I have f of x equals x squared, f of 1 is going to equal 1. I guess I should also say f of 0 is going to be 0 squared, which is 0. F of 1 is going to be 1 squared, which is 1. F of 2 is going to be 2 squared, which is 4. F of 3 is going to be 3 squared, which is 9. And then what I'll also note is that f of negative 1 is equal to negative 1 squared, which is positive 1. F of negative 2 is negative 2 squared, which is positive 4. And f of negative 3 is negative 3 squared, which is positive 9. And so we're seeing these coordinate points here, right? Remember, we have our input 1 and we have our output, excuse me, let me re-say that. I misspoke. We have our input negative 1 and we have our output 1. And so I'm going to come on over to negative 1 and I'm going to come on up to positive 1. And that right there is my point that I care about in the blue. And then we've got all these other points that I've listed here: 2, 4, 3, 9, negative 2, 4, negative 3, 9, 0, 0. So we've got all of those points right there. And if you sort of connect them in the appropriate way, if you were to keep plugging in x's and keep getting out y's, it would look like this red graph right here. So this is the parabola. It opens upward. We're going to talk much more in depth about parabolas in the next lecture. But yeah, this is just sort of the basic idea of what a parabola looks like. Let's continue on. Square root function. It kind of looks like a parabola, but turned on its side. You could envision something like this, and that kind of looks like a parabola turned on its side. And for this, we're just dealing with the top half right there. Again, you could plug in a bunch of different values in for x. I've plugged in 1 and I get 1 out for y. I plugged in 4, and when I take the square root of that, I get 2. I plug in 9. When I take the square root of that, I get 3. And you've got your points here, and you can, sort of connect the dots, and there you go. You've got your square root function right there. So that's just kind of this idea of the square root function. Let's move on to the inverse. This one is tricky. And remember, we've talked about domain, and we've talked about why, we've talked about these common times and common scenarios when we have a problem with our domain. And one of those is when we divide by 0. And so what I want you to notice here is that because I have a 1 over x, if x is equal to 0, that means that I would have a division by 0. And that's bad. Bad. We can't do that. We can't divide by 0. And so what that means is, in the sense of domain, is we're not allowed to plug in x. X equals 0. We're not allowed to plug in 0 for x. And so what I notice here is when x is equal to 0, that's right here. I haven't moved left or right at all. I'm not over here. I'm not over here. I'm right smack in the middle, right there. And you'll notice here that at this x coordinate, there is no y value that the function corresponds to. There's no y for that x, and that's because we can't divide by 0. And so what we might do is we might actually put an asymptote right here. I'm not going to get into too much about what that means and everything. If you're familiar, great. If you're not, that's okay. Really, we're just saying that, hey, the function doesn't exist there. And so what happens, if you just plug in a bunch of values in for x and get your y values out, if I plug in 1 for x, I'll get 1 for y. If I were to plug in 1/2 for x, let's do a different color here. If I were to plug in 1/2 for x and I were to go up, I would get 2 for y. And then if I plugged in 1/4, I would end up getting 4 for y, and so on. And this thing just keeps kind of going up and up and up and up as we get closer and closer to 0. And same thing on the other side. It's just everything's negative over here. We just go down and down and down because we get our y value would get more and more negative. So inverse right here looks all great. This is what an inverse function will look like right here. While I actually have been on this topic of domain, I want to go back here as well and remind ourselves that we talked about that we can't have a negative in underneath the square root. So that means that x can't be negative. And what you notice here is that it's not, right? I don't have any x's in this region over here for all, or I don't have a function over there because the function isn't defined over there. Because I'm not even allowed to plug in a negative x, I can't have any part of my function be on this in this entire region over here. It just doesn't work because I can't plug in any negative x's. 0 is the smallest x that I can plug in. And that's why I start right there. Let's do that in a different color. That's why I start right there on that orange dot, or orange X marks the spot. That's right. That's where I'm starting, right there. Instead of an X, let's make that a star. That's why I start right there. Awesome. So exponential function. So I've chosen to graph e to the x here. You could have graphed 2 to the x. You could have graphed anything that is, so long as it is a number raised to x. But I've chosen to use the number e. And in this case, what we have here is we have the graph sort of just skyrocketing up. It just increases and increases and increases, and it keeps growing and growing and growing and getting larger and larger and larger. And a couple things to note here. We do have a y-intercept at 0, 1. That should be pretty clear. If I do f of 0, right, we plug in 0 for x, then I get out 1 because anything raised to the 0 is equal to 1. And so I get my y-intercept there. Well, another thing to notice is that there is no x-intercept. While it might look like it here, that's just sort of, this is sort of just not zoomed in necessarily. It looks like this is touching, but it never actually quite touches. If I were able to keep on zooming in and in and in, you would notice that it never actually touches that x-axis in black. It gets really, really close, but it never quite touches it. So there is no x-intercept here. Again, if you're familiar, I could put an asymptote right there. Just all that means is that the function doesn't cross that line, that dashed line. So we've got our asymptote right there, and what another thing I want to point out here is and explain is why the graph has such small values for very negative x. And let's do an example. Let's plug in f of -4. If I do that, I get e to the -4. And remember, with a negative exponent, that's the same as 1 over the positive exponent. So this is the same as 1 over e to the 4th. And recall that that e to the 4th is just 2.71 to the 4th. And so if I were to actually do this, we would get something like 54 roughly for e to the 4th. I'm approximating it there. But basically, this is like, let's say approximately 1 over 54. And that's really small. That's approximately like 0.02, just very roughly. I'm just estimating off the top of my head here. So that's a very small y value when I plug in x equals -4. And that's why you can see down here, when x is equal to -4, when x is equal to -4, we end up having a very, very small y value. And so yeah, there we go. That's an exponential function. So let's go ahead and now that we've seen all these functions here, let's get into certain words that we can use to describe a function. And I want to start off with increasing and decreasing. And so when a function is increasing, what that means is that as x gets larger, so does y. An alternative way of saying that is as x gets smaller, so does y, right? It basically, y does whatever x does. If x gets bigger, so does y. If x gets smaller, so does y. And then decreasing is just the opposite. If x gets bigger, y gets smaller. If x gets smaller, y gets bigger. And there we go, we've got that right there. But this is best done by just looking at an example. Let's look here at x squared. What I notice here, as x gets bigger, I am going to read across from left to right. So I'm going to start over here and I'm going to read from left to right because that's my x getting bigger and bigger and bigger. I'm starting very negative and I'm going to until it gets less negative, it gets to 0, it gets to a positive small x, it gets to a positive large x. So it's getting bigger and bigger as I read from left to right. And when we look at this idea of increasing and decreasing, our question that we want to ask ourselves is, what does y do when x gets bigger and bigger? So as I move from left to right across this function, let's go ahead and let's put this in green here. As I move from left to right, what I notice here is that my function, it's going down here as I read from left to right. That means that this function is decreasing on the left half. And on the right half, the function is going up as I move from left to right. Always keep that in the back of your mind as you move from left to right. And so it would be increasing on the right half. So let's go ahead and make a note of that. Decreasing on left, increasing on right. If you read from right to left, everything will be flipped, obviously. So don't read from right to left. Let's continue on, some more examples. I've got root x. As I move from left to right here, I notice that my y values, they get bigger and bigger, right? You can see that they get larger and larger. I'm moving up, if you will. As I read like a book from left to right, my function moves up. So that means that this function is actually increasing for all x. And so there we go, increasing right there. This is a tricky one. If this guy is increasing or decreasing, or a combination of both, let's sort of look at it and think about it. I'm going to read from left to right. And so we're going to start over here. And what I notice is that my graph is going down. It's getting more and more negative, right? As I follow along on this. And so that to me makes it seem like it's decreasing. Well, then we hit this point where I have that thing that we called an asymptote right here, where the function isn't defined at 0. So I don't really have to worry about 0, but let's just kind of move just onto the other side of the wall, if you will, and look over here. So if I start up here, what I notice is that my function is going down here as I read from left to right. And so in this case, the function is actually always decreasing. Always decreasing right there. And so this one may not look like it's always decreasing, but it definitely is. Right here, second to last example, f of x equals e to the x. This one should be fairly straightforward now that we've seen this. As I read from left to right, my function is going up. The y values are getting larger as I move from left to right. So this is increasing for all x. Last example here, and this is a tricky one. I have the function f of x equals 3. So it's just a straight line at 3 right here. 1, 2, and 3. So then in that scenario, we don't really, as we read across from left to right, my function doesn't get bigger and it doesn't get smaller. So in this case, we actually can't say whether it's increasing or decreasing. What we answer is that this function is constant here. And so that's that other word. If something is not increasing or it's not decreasing, we call it a constant. Great. So let's go ahead and look here at another descriptor of how we can talk about a function, and that'll be maximums and minimums. And so we're going to talk about two different types of maximums and minimums. The first will be an absolute max or min. And when we say absolute max or min, that is just the largest or the smallest y value that the function attains. Doesn't matter, just look at the entire graph, and whatever the largest y value that it attains is, that's going to be the absolute maximum or the absolute minimum. And so let's actually go ahead and look at a couple of these examples here. Let's skip over that. Let's look here. So right here, the absolute minimum should be very easy. The smallest y value that this graph attains is just 0 right there. And I'll mark that with that green line. So the minimum, the absolute minimum would be 0. The absolute maximum is a different story, however, because this function is just going to keep going up and up and up and up and up. It's not going to stop. And so in this case, we actually don't have an absolute maximum. The function never stops. I mean, maybe you could say the maximum is infinity, but that's not really a number. So we actually don't have an absolute maximum in this case, but we do have a minimum. So let's go ahead and let's look at another example here. Again, here, the minimum is going to be 0. That's the smallest y value that it attains here. And in the same vein, this is going to keep going up and up and up and up. It's going to keep on going, and we actually don't have an absolute maximum. Another example here, we've got, we actually, in this case, don't have a maximum or a minimum, because this function is going to go down forever here, and it's going to go up forever here. And so there is no maximum or minimum example or value, if you will. Let's go ahead and look here, the maximum and minimum. Maximum is pretty easy. We kind of see, actually, this happens to be a trend a lot of the times where we haven't had any absolute maximum so far. That's just coincidence. But here we don't have an absolute maximum because the function just keeps going up. But the absolute minimum is a trickier case here. Like I said before, this function goes down and down and down, but it never quite touches that x-axis. So a lot of times when I ask what is the absolute minimum, a lot of people will say 0. And that's actually a problem, because the thing here is that the function never actually reaches 0. And so really what's going on here is I'm going down and down and down and down, but I never actually reach a smallest value. I keep going down forever, and I'm never quite approaching 0. Well, you might ask, well, how can you go down forever but never actually cross, the wall or something like that? Well, think about it this way. If you stood on one end of a room and you walked halfway towards the other end, So you walk halfway towards the wall. Okay, now you're halfway there, great. But now from where you're standing, if you walk halfway again, and then from where you end up, walk halfway. Keep walking halfway each time. You're never actually going to touch the wall. You're just going to get closer and closer to it, and you'll never stop moving. You're always moving halfway closer, but you never actually touch it. And that's what's going on here. So we don't actually have an absolute minimum in this case. Right here, again, for this constant function, we would just say the maximum and the minimum are both 3. That's the largest as well as the smallest value that this function attains. So there's absolute maximum and minimum. I now want to talk about this idea of local maximum and minimum. And there's it's kind of difficult to explain this in a simple way by using textbook definitions. What I like to just do here is just say the local max or min of a function is the largest or smallest y value that the function attains locally. And just think about that word local, where it's saying like nearby. And so let's look at this example here. If I have a function that looks like this, we can very clearly see that the absolute maximum and the absolute minimum aren't going to exist. They're just this function just keeps going up to infinity and it also keeps going down to negative infinity. So there is no absolute maximum or minimum. But what I notice here is there are some points here where the function is sort of at a peak. It's at its largest in a small little region, right? If I look at this point right here, and I just look nearby it, that's the largest point. It's almost like a hill before you reach the top of the mountain. This point right here is the largest point nearby. It's the largest point locally. So what we would say is, yeah, this point right here is a maximum, but it's not an absolute maximum because there's clearly other coordinate points that are bigger. I mean, all of these blue dots that I'm writing are bigger than this starred black dot. But locally, just in a small little area nearby, it is the largest value there. It's almost like I've just crested the hill and I'm going to go back down before going up again. So nearby, that is the largest value. So we would call that a local maximum. And the same exact thing happens there, right there, where we have a local maximum. That is the largest point in a very small nearby area, just almost like within arm's reach, if you will. And then what we have here, I'll star it, we have local minimums, where they are the smallest point, just in a nearby area. And so there we go. Yeah, local minimum right there. A lot of these examples that we've looked at, the absolute maximums and the absolute maximums and the local maximums and the absolute minimums and the local minimums are the same. So I don't think it's really worth going through these examples. Really, it's just if you have a function that kind of, wiggles its way around like that, then you're going to have some local maximums and local minimums, as well as obviously absolute maximums and absolute minimums. So I'll just sort of sketch one quick example here. Let's say I have a function and it looks like so. Let me make sure my labels are good. X and Y. And if my function looks like this, and let's just say actually, let's do this. And then it just stays just straight constant. It just goes on forever like that. In this case, I would have an absolute maximum and an absolute minimum right here in green. These are the largest and the smallest y values that the function attains. So that's just the absolute max and the absolute min. But then I would also have local maximums and local minimums. And then as well, This is also a local max. That should be pretty clear. If it's an absolute maximum, it's definitely a local maximum. It's the largest value nearby as well as just the largest value overall. Just because something is an absolute max or min doesn't mean it can't be locally max or min. It actually should be. But we also have these local maxes over here. That's really what I want to focus on right there. They're the largest value of the function in a nearby area. And so they will be local maxes and mins, labeling f of x here in the red. I'm not going to worry. Some people, they might ask about this point over here and this point right here and what happens there. I'm not really going to focus too much on that right now. I don't really care too much about that. We'll just mostly focus on these green and blue points that I have labeled there. And that's kind of your difference between absolute and local maximums and minimums. So that'll be it for the lecture. We've got some common functions that we now can recognize when we see them in the future. And then we have a couple ways that we can describe functions. We can say they're increasing or they're decreasing. We can say where maximums and minimums are, and we can even define those maximums and minimums as being absolute or local. So we'll go ahead and call that for the lecture, and that'll be it.